Okay, so probably no surprises here. Everything's pretty much straight out of your notes. 4 components of climate are? Right, light, wind, precipitation, and temperature. Okay. One mark each. Okay, what's the most important factor affecting climate for any location on Earth? I think I only said that about, what, 7 or 8 times in the first day. It is? Starts with L. Latitude, right. Okay, that affects every place because every place has some distance from the equator, or maybe it's right on the equator, okay, but your distance from the equator affects the amount of sunlight you get, and that affects everything else. Okay, number 3, what factors affecting climate most make Victoria's climate different from Calgary's? 2 things. Where is Victoria? Right by the ocean. Where's Calgary? Not by the ocean. Okay, so proximity to oceans would be 1. Okay, if they have something about being close to the ocean. Okay, that's 1 mark. What's the other thing that's the big difference? Altitude. Now, I would say, a lot of people want to say, well, presence of mountain barriers. Well, presence of mountain barriers actually affects both of them. We're just on different sides. Okay, they get the effect of being on the windward side. We get the effect of being on the leeward side. But I know probably a lot of people were thinking that, so I will also accept mountain barriers. Okay, since it is true, we get different effects from the same thing. Okay, so I'll say mountain barriers as well. So it's out of 2 marks if they have 2 out of the 3. Okay, you can give them 2 marks. Okay, questions there? All right. What part of the Earth is most responsible for distributing solar energy? Said that about 5 or 6 times yesterday. Of the 3 spheres, the most important sphere is the atmosphere. Okay, what process is most responsible for transferring solar energy from one place to another? We learned about 3 processes: conduction, convection, and radiation. Which one's most important for Earth? Convection. Okay, because it's the one that can transfer energy over the largest distances on Earth. Okay, obviously radiation gets here from the sun. Okay, that's a great distance, but we're talking about just within the Earth here. Okay, number 6, what process transfers energy by waves? Gave it away, it's radiation. Okay, and within the lithosphere, what process transfers energy? The lithosphere is solid, and we've named 2 out of the 3 already. Conduction. All right, it's out of 11. Okay, give them a mark out of 11. Let them see it. Put it in the box, please. Then take out your notes package to lesson 4 from this unit. All right, so yesterday we talked about conduction, convection, radiation. We talked about how heat is transferred on Earth. Okay, now we're going to look at the specific effects, okay, of the main method, which we just said in the quiz was convection, okay, for transferring energy to various places on Earth. All right, so what we're going to look at now is how that, what are the results of that convective process? And we said yesterday that convection within the Earth's atmosphere is also known as, someone whispered it or mumbled it. I thought I heard someone whisper or mumble it. What's moving air called? Okay, good. Somebody knew it because we get a lot of it here. Okay, wind. All right, convection, moving air is wind. We got to look at how does that work on Earth, because there's patterns to the movement of air on Earth. I mean, certainly there's, things that happen, you hear these things on the Weather Channel like the Polar Vortex and Snowmageddon and things like that. Okay, yeah, there are certainly freak occurrences that disrupt the sort of normal or prevailing conditions. Okay, that's part of a complex system. But for the most part, okay, we can predict what kind of winds we're going to get in an area based on where you are. Okay, so we're going to look at why that is. Why are our prevailing winds out of the southwest, whereas if you go up to Fort McMurray, they more often are out of the northeast, okay, and things like that. So that's what we're going to kind of look at here. Okay, so we want to understand how energy is distributed on Earth. Now, in terms of getting the energy, where does the most energy strike the Earth? On the equator. Okay, it's getting the most direct overhead sunlight all the time, and the closer you get to the poles, the less direct that is. Of course, the Earth wobbles back and forth, okay, on its tilted axis, which changes the seasons. Okay, but for the most part, near the equator, you get the most energy. Okay, we need to understand that the role that winds play in distributing that energy, because obviously the second law of thermodynamics is still in effect with a big system like the Earth. And if there's more energy hitting the equator, it has to move away from the equator, obeying the second law of thermodynamics. Heat flows from hot to cold. Okay, we have to look at something called the Coriolis Effect. Okay, and the Coriolis Effect is something that causes a deflection of winds. Okay, and it has to do with a combination of wind and air trying to move one direction, but the Earth spinning underneath it as it tries to do that. All right, everyone follow me there? It would be like if you had like a globe, okay, and you were spinning it and trying to write on it, okay, or trying to draw a line straight from the equator to the pole while it was spinning. Would you be able to draw a straight line? No, okay, and that's kind of what the Coriolis effect is. It deflects winds, because winds are trying to do just that. They're trying to move in a straight line, but the Earth spins underneath them as they're trying to do it. Okay, and then lastly, recognize that global wind patterns are a product of, okay, convection and the Earth's rotation. It is the combination of those two things. All right, so second law of thermodynamics causes the convection, and the Earth's rotation causes the movement of air in sort of different directions rather than straight lines. Okay, so distributing the Earth's energy budget. Okay, we said at the equator we get the most energy. All right, so the Earth's atmosphere has to always be moving. Okay, because there are differences in energy, and anytime there's differences in energy, there's movement. Okay, movement of energy usually involves matter moving as well. That matter is going to be the air. Okay, now you can see here that the Earth rotates this way, according to this line here, which might be hard to see, so I'll make it green. Okay, the Earth rotates this way. All right, which is why when the sun rises, it rises in the east. So if we were right here, which we were like, what, 10 minutes ago, okay, when the sun finally came up, okay, as we're coming into the sunlight, okay, we would be looking to the east and the sun would appear to rise there, okay, and then the sun goes overhead. To us, it looks like the sun goes this way, but it's because we're rotating under it, okay, and then when we get over here, the sun's to our west and sets in the west. If you didn't know that, now you do. Everybody with me so far? Okay, now what that does is it's kind of like if you're driving in your car in the summertime, because you obviously wouldn't do this in the winter, okay, and, well, you shouldn't do it in the summer either, and you stuck your head out the window, okay, because you shouldn't do that, okay, but if you stuck your head out the window in a moving car, it would feel what? Windy. Is it necessarily windy? No, it's not, but you're moving through the air at whatever speed your car is going. Okay? Well, it's sort of that way with the atmosphere and the Earth. The atmosphere and the Earth are not a solid connection. Okay? They're somewhat connected. They kind of follow each other, but there's a bit of a drag. Okay? So as the Earth spins, the atmosphere, it kind of spins under the atmosphere. Okay? So it's like you're moving through the air all the time, like in a moving car, but not that fast. Okay? The atmosphere moves with us to some extent, but not always perfectly in time. Everyone follow? Okay. So what that creates is a kind of a deflection. So if we've got air moving away from the equator, okay, so this would be like hot air moving away from the equator, okay, we would also have cold air coming back towards the equator, right? But because the Earth spins under it when it's trying to do that, it makes it appear as though it's coming from a different direction. Okay, everyone all right with that? Okay, so here's what's going on. I'll draw this a little bit better. Okay, hot air. Is it going to be higher or lower than the cold air? Will hot air be on top or on the bottom of cold air? on top because it's less dense, right? Hot air rises, cool air descends. All right, so when sunlight strikes the Earth's equator or the Earth's surface anywhere, the hot air rises, okay? And as it rises, it moves to the north, okay? The cold air comes in to replace it, like so. But the Earth rotates underneath the atmosphere. So this cold air that's coming down because it's closest to the surface is the wind that we would feel. It's supposed to be coming straight out of the north. But as it tries to move from north to south, the Earth spins underneath it. And it makes it appear as though it's doing this. Okay? Which would make the wind feel like it's not coming directly out of the north, but out of the northeast, because it gets deflected a little bit. Okay? At the equator, these are called the trade winds, and they generally blow from east to west. Okay? Slightly northeast to southwest, but generally east to west. Everyone with me on that? Okay? Now, on our part of the world, since we can't see it on there, okay, a little further north, so the trade winds, here's the equator. Okay? The trade winds kind of happen between these two latitudes. Okay? About 30 degrees or so. Right? Above that, okay, is where we are. Okay, and we're right near the transition zone. Okay, but okay, there's another set of winds that happen in this set of latitudes here. Okay, what's happening there is that warm air that went aloft from the equator, okay, it went this way, and now it's gotten to this point and it's starting to settle because the cold air has moved underneath it and there's nothing to hold it up anymore. So it starts to settle a little bit. Okay? As it does that, the Earth is still spinning underneath it and pulls it along. Okay? Because now as that air, instead of going to the south, is kind of moving to the north, it goes with the rotation of the Earth. And you get this kind of a wind happening. Right? Now, what direction does that seem like the wind would be coming from? Southwest. Is that where our winds generally come from? Yeah, okay, they come out of the southwest here because we're just in that part of the world where typically winds are out of the southwest. If you go just a little bit further north, like let's say you get to about Fort McMurray, that's about where this line is. It's not a hard and fast line, but it's reasonably distinct. Okay, well, when you get to that line, this warm air is kind of gone. Right, it's kind of done its job and transferred a lot of its energy. So what you get is more of a spinning near the top, okay? And that creates the same effect it had down here. Cold air tries to move south, okay, while interacting with this last bit of warm air and gives you the same effect you had here at the equator. Okay? In the southern hemisphere, okay, it works kind of the same way. Okay? Winds go like this. Okay? And whoops, I drew that one wrong. I never think about the south because I don't live there. There, that's better. Okay, and then we would have this one doing that. Okay, so you get this kind of banding. We don't see it because our atmosphere is transparent. Okay, so it's not really evident unless there's a big storm, and then we can track the big storm moving according to those winds. Ever watch hurricanes when they land on land in like Florida and places like that? Okay. You never see a hurricane move away from Florida. Okay? They never go out to sea because the prevailing winds are always drawing them from east to west. Okay? They're always blowing onto the land at that latitude. But, okay, if you watch air movement here, okay, when that hurricane kind of hits land and it comes in and moves in and then it gets to a certain point starting to fizzle out, it actually starts to turn and go back the other way as it dies because it gets across this latitude and actually gets kind of torn apart and then blown back out to sea. Everyone follow me on that? Next time you see, like you watch the Weather Channel, you can actually watch the movement of clouds going in opposite directions at certain latitudes. Okay, I'm going to show you actually a video of Jupiter where you can see that almost perfectly. If you've ever seen Jupiter, it's got like bands of gas, different colors. Okay? If you actually watch it in motion, it looks like part of the planet is going this way and part of the planet's going the other way. And there's like 4 different bands all the way up. Okay? And it literally looks like parts of it are spinning in opposite directions. Okay? Because the winds are so distinct and so strong. All right, everybody with me there? I explained the Coriolis effect a lot earlier than I usually do, but I had a thing in my head. Okay. All right. So the Earth's atmosphere is always moving, and that creates these winds. Okay. So the reason there's wind is because there's unequal distribution of solar energy. Okay? If there's unequal distribution of energy, nature tries to equalize. Okay? And it equalizes with the second law of thermodynamics, convection, okay? And we get wind. Okay? All right, so was talking about this here, this movement of air, all right, that we sometimes see on the weather maps. Okay, and if you had a hurricane kind of coming in, okay, the hurricane would always kind of move in this direction, okay, kind of make landfall, and then it kind of does this. Okay, and its track always kind of goes like that. It comes in on the last bit of those easterly winds, okay, and then the westerlies kind of push it out over the Atlantic provinces where it usually dies. Right. Now, one of the big wind patterns that we get on Earth, okay, is called the jet stream. How many people have heard of that? Okay, all right, good. So a few people have heard of it. Okay, it's a very high altitude, very high speed wind. All right, and its location is always changing. Right, it's based on centers of high and low pressure, and they can push the jet stream around. Okay, and they always do. In fact, when I was coming back from my vacation over Christmas, I got on a flight where we had to cross the jet stream. Okay, and I thought I was going to die. Okay, I thought I was going to die in a plane crash that day because we got to spots where suddenly the plane would drop. And I mean, not drop a little, like it dropped several hundred feet, just all of a sudden gone, and my iPad flew off the tray table. Okay, because the plane dropped and my iPad tried to stay still. Okay, it literally levitated in front of my face for a second. Okay, so you get these really rough air patterns because there's this wind you're trying to cross. Okay, and that's what the jet stream is. Lots of times, planes will intentionally fly into the jet stream. Okay, if they're trying to fly, let's say from Los Angeles to New York, get in the jet stream because it's blowing the right direction. Okay, they'll intentionally fly in it and go with it. Then it's not as bad. But when you try and cross it, that's when you get really bad turbulence. Okay, everyone follow me so far? Okay, now what this jet stream does is because it moves around a lot, it can really influence your weather. Okay, right now the jet stream in this picture anyway. Okay, we got the jet stream moving in off the ocean. Okay, up here towards the bottom of Alaska and northern BC and that kind of area. Okay, is this going to have warm or cold air? Warm. It's coming off the Pacific. Okay, it's probably also going to have a lot of moisture. Right. So as that gets in towards here, towards this warm and dry area, okay, well, you might get some storm activity. Okay, in this kind of an area here. Now, as it goes over here, it's obviously going to cool off because now it's up by Alaska, it's over the the Arctic Ocean and that kind of area, and then it's coming down through this chilly air that's forcing the jet stream back the other way. Okay, because air always rotates a certain direction around a high pressure area. Okay, so it's pushing it down and around this way. So right here where we live, what kind of weather are we getting? If the wind here is coming out of the northeast, is it good or bad for us? Bad. Nothing good weather-wise ever comes from that direction. Okay, we're going to have this warm, dry air mass interacting with this really cold air mass, and you're always going to have like either strong winds or the potential to have unsettled weather. Okay, and you can see that same thing happens over here. Okay, as the jet stream swings out and then comes back across, it's going to pick up some moisture and then go back into here where it's going to have unsettled area. Now, in this unsettled area, what do we call this area right here that goes through the kind of northern central United States? It would include places like Kansas, Oklahoma, Ohio. Yeah, Tornado Alley. You guys heard that term? That's Tornado Alley. Okay, and that's because the jet stream very often runs right through there. Okay, in the summertime, and that can cause very unsettled weather. Right. So anyway, the jet stream, because of its kind of wicked and almost unpredictable movements, can really cause exchanges of energy. Okay, because it's going from hot to cold and then back to hot, and it's always bringing these air masses with it. Okay, so it's a really important mechanism for transferring energy from equatorial to polar regions. Okay, we don't feel it on the ground because it's a very high altitude wind. Okay, but it still moves a lot of energy for us that we don't necessarily feel. Okay, so jet stream, pretty important. Okay, transfers a lot of energy between polar and tropical regions. Questions on the jet stream? All right, now here's the diagram I was drawing. Aren't you glad I had a real picture of it, because it's much better than what I can draw? Okay, so we've got, okay, the Earth's bands of wind. Okay, these bands of prevailing winds. Now, near the equator, okay, we've said that hot air rises, so it comes up, and then it tries to move northwards. Okay, as it's moving northwards, cool air, okay, is trying to move in to replace it because it's more dense and it's down below. As it tries to move south, the Earth spins under it, okay, and causes it to get deflected, and we get what we call the trade winds. Okay, they were called the trade winds because way back when all the Europeans were coming to the States, that's how they would get there. Okay, on their big sailing ships, they would use the trade winds to take them there. How do they get back to Europe then? Because you can't sail against the wind. Yeah, you'd sail in on the trade winds, okay, and you'd end up down here, and then you'd sail north along here and go back to Europe that way. So you would have to, from Europe, you would have to sail from, like, let's say England down to, like, Spain, okay, or maybe even a little bit south of Spain, and then catch the trade winds, and then sail up the coast of North America back to get the westerlies, and then, okay, you can get back to the old country. Okay. Everyone follow me on that? All right. So what we see is, between these two latitudes here, we get northeasterly winds. Okay, between these latitudes, okay, between about 30 and 60 or so, okay, we get southwesterly winds, and then you get polar easterlies here. And this is what they often refer to as the polar vortex. Okay, you guys heard that on the weather? Okay, they always talk about the polar vortex because it sounds cool. Okay, but really what it is every planet that spins and has an atmosphere has a vortex at the poles. Okay, it's just a natural occurrence that happens. Once in a while, that vortex increases in size and strength, and its effects can be felt further south than normal. All right, so when we're about to get, like they were predicting that snowmageddon, okay, like right around Christmas this year, that's what they were saying was going to happen, is the polar vortex was going to get bigger and stronger, come a little further south, and interact with warm air coming up from below and create lots and lots of snow. All right, everyone okay with that? Okay, so it's this pattern of air movement combined, okay, with the rotation of the Earth that we call the Coriolis effect. Okay, so again, kind of same thing here, same explanation. Okay, as the Earth is spinning, okay, as the Earth is spinning this way, the air is trying to move, okay, in other directions, and it gets deflected. So really, we see right here, okay, these tubes are really just a convection current. All right, we've got hot air right here, hot air rising and moving north. Okay, because it's nice as a three-dimensional diagram. Okay, and then here, okay, we've got the cool air moving south. Everyone okay with that? Okay. Now when we get here, okay, we kind of get a reversal of that happening. Because this air has been moving really, really fast and it has to drop, okay, it kind of gets underneath, okay, some of this other air, all right, and creates kind of the opposite effect, and then we get, okay, those southwesterly winds there, and then you got the polar vortex at the top. All right. Okay, so just showing you a picture. I'll show you a video in a sec. Okay, you can see those bands on Jupiter really, really well. Okay, it's got way more, okay, than we do, right? Just because it's so much bigger, right? So you got your equatorial region, okay. Here's the rotation of Jupiter, okay. So you'd see that these bands are going to kind of go this way, and then you'll have bands going this way, and then bands going this way, and bands going that way, bands going this way, and so on. Okay, so you'll get this really wicked, okay, rotating effect. Right? Okay, so we kind of see there how that rotation, okay, can affect the wind patterns, all right? And you could see very clearly on several of those videos where right next to each other we had winds going west and winds going east, okay, just below or just above. Okay. All right, now the Coriolis effect, okay, that we talked about there just a little while ago, okay, we said that as the Earth is spinning, okay, and something's trying to move from north to south or south to north, it's going to get deflected, okay? And so if the Earth is spinning this way, according to this red arrow down here at the bottom, okay, and something tries to move from the north to the south, it's going to appear as though it's doing this to someone that's on the surface of the Earth, okay? In terms of the atmosphere is really actually moving from north to south. Okay? But because the Earth spins underneath it, those of us on Earth have that sticking your head out the car window kind of feeling, and that it's being pushed in another direction because we're moving through it as it's moving north to south. Okay? Everyone follow me there? All right. I want you to answer, okay, those 4 questions here. I'll give you a couple minutes. Okay, answer those, and then we'll go over them, and then we're going to move on to specific heat capacity today, okay, which is pretty easy actually. Okay, so we'll get well into that today. All right. So let's have a look at these here. Okay, so it says for number 1 here, describe the effect of unequal distribution of thermal energy on Earth on the temperature of the atmosphere. Okay, so if the atmosphere is warmer at the equator than it is at the poles, what's going to happen? That's a D. Okay, now it looks like a B. All right. Second law of thermodynamics. Energy moves from hot to cold. If energy is moving from hot to cold through the atmosphere, we call that convection or wind. Okay, that's what the effect of unequal distribution of solar energy is on the temperature of the Earth's atmosphere. The Earth's atmosphere wants to equalize the temperature if it can. It can't. Obviously, it's always going to be colder at the poles and at the equator. But that's also why the Earth's atmosphere is always in motion. Okay, everyone follow me there? Okay, so those are the key things. Second law of thermodynamics, heat flows from hot to cold. Okay, that's convection in the atmosphere because it's a fluid. Okay, and that means wind. All right, explain how the Coriolis effect influences the direction of winds in the northern hemisphere. Okay, well, it deflects them as they move from north to south. They get deflected to the west. If they're moving from south to north, they get deflected to the east. Okay, a wind that is blowing east is called a westerly. That seems weird, right? Because it's blowing from the west. Winds are always named by what direction they're coming from. Okay, so wind is out of the west blowing east, it's a westerly. Okay, if a wind is out of the east and blowing west, it is an easterly. Everyone with me there? Okay, just know that a wind is always named by what direction it comes from, not which direction it's going. Okay. All right, number 3. Okay, what are the trade winds? Okay, well, they're easterly winds that are where? At the equator. Okay, they are equatorial easterlies. Okay, and what are jet streams? Somebody's got to know the answer, especially since it's in your notes. Right. Okay. And not just a major wind, but the key part that makes them different from these prevailing winds we talked about is that they are at a high altitude. Okay, they are high altitude major winds, okay, that help transfer energy from polar and equatorial regions. Okay, is their location always the same? No. Okay, they're influenced by where the high and low pressure is, which is why they can sometimes have really radical shapes. Okay, sometimes they just blow straight across the continent. Okay, that happens, and it happens fairly frequently, which is why they can consistently be ridden, okay, by eastbound aircraft. Right? But sometimes they get pushed and then they end up going north or south, and if you have to cross them in a plane, you're in for a wild ride. Okay? Especially if you have to land, okay, in that area. Luckily, do jet streams usually affect a plane when it is landing? No. They're high altitude winds. Okay? So luckily they're not usually a problem when you're landing. Okay? However, they make the descent fun. And I say fun. Okay? Being facetious. All right, everyone with me on those things? These are definitely multiple choice type items, okay, for your unit exam.